This is a follow-up video to the Safe Drinking Water Act Part 1. In that video, we reviewed the 4 or 5 general steps that the EPA undertakes when setting a new regulation or numeric criteria. These are called maximum contaminant level goals and maximum contaminant levels. Here I'll go into a little bit more detail on how those MCLGs are set. First, let's review the setting of the MCLG for a non-carcinogen. The first step is for the EPA to conduct toxicity studies to determine the no observed adverse effect level. At this dose, which has units of milligram per kilogram per day, the acceptable daily intake can be defined. This dose can be converted to a drinking water equivalent, DWEL, considering or assuming that a 70 kilogram adult consumes 2 liters of water per day and there's a lifetime exposure, or 70 years. If you take this and you look at the CDI calculation, you can determine the concentration of water times the exposure duration, the exposure frequency, etc., divided by the body weight and the averaging time, which here would be 70 years. So using the reference dose and those assumptions, you can find the DWEL, or drinking water equivalent. Now the reference dose is based on all exposure pathways. And so this concentration must be scaled for just the exposure taken up in drinking water. So the DWEL is multiplied by the percentage of that dose associated with drinking water. In this way, the EPA can determine a concentration in which no adverse effect should be incurred by the population. Now for carcinogens, the maximum contaminant level goal is always set to 0, and this would be for class 1 or known carcinogens. For possible carcinogens, or class 2, the reference dose is divided by a safety factor or conservative factor of 10, or the level is set such that the risk incurred would be no more than 10 to the negative 5 to 10 to the negative 6 for lifetime daily ingestion. When setting the maximum contaminant level, the EPA must set the MCL as close to the MCLG as is feasible or reasonable. This takes into account the cost of treatment, certainly, but also the detection limit, the treatment process capabilities, and the natural levels found in drinking water. For instance, the EPA could determine that we would like to have less than 1 microgram per liter present, but we may only have the analytical capability to measure 10 micrograms per liter. If this is the case, setting a limit of 1 microgram per liter is meaningless, and the EPA has to resolve this difference. The Safe Drinking Water Act also stated that the EPA needed to determine a best available technology for each regulation that has an MCL. The BAT is usually not required to meet the MCL. For instance, if the MCL is already met, the EPA typically doesn't care what technology was used to get there. Or, in the example below, the treatment is not necessary at all. The BAT to remove volatile organic carbon, or VOCs, is granular activated carbon, GAC, or air stripping. If a water source does not have VOCs to begin with, the treatment plant is not required to utilize the BAT. When it is not practical for the EPA to set a maximum contaminant level, the EPA requires a specific treatment technique, and this is given the acronym TT. An example of this is that viruses are not required to be measured. It's actually very costly and difficult to measure viruses in the laboratory. So instead of setting a numeric criteria, the EPA requires that all drinking water be disinfected and must meet something called CT values. And we will review this when we do drinking water treatment. This is a table of regulations set under the Safe Drinking Water Act, and these are all for primary standards. You can see here that the maximum contaminant level goal and the maximum contaminant level and the BAT are defined for each of the contaminants. For many things, the goal is 0, or there is a treatment technology specified, or the goal has a number and the maximum contaminant level is higher. You should recognize that the maximum contaminant level goal is always set less than or equal to the MCL. The next table, which is also primary standards of the Safe Drinking Water Act, shows you the microbial contaminants. There are many microbial contaminants and viruses that are listed here. All of these require treatment technology, which would be disinfection and CT times. I'd also like to point out here that for the best available technology, there were many acronyms used, and these are defined under the table. In the next few slides, I'll review a few specific aspects to the Safe Drinking Water Act. The first is the lead and copper rule. The lead and copper rule is a little bit different than the primary standards, which are all measured at water leaving the plant. The lead and copper rule pertains to premise plumbing, because mostly lead and copper have to do with the homeowner's plumbing. In a regulation released in 1991, the goal for lead was set to 0 parts per million, but the actionable level was set to 15 parts per billion. The goal and the limit for copper were both set equal to 1.3 milligrams per liter. The fact that these standards apply to the tap have caused some issues for the EPA, both in terms of monitoring, but also in terms of what to do if the levels are exceeded. In the regulation, a utility must sample a certain number of taps per year, and those taps depend on the size of the system. And Lawrence were required to measure 60 tap water samples every 6 months. If more than 10% of those tap samples exceed the maximum contaminant level, or the difference between the treated water at the plant and the tap water is greater than 5 micrograms per liter, then the utility must implement corrosion control measures. What this also states, if less than 10% have high levels, the utility can do nothing. Now, these samples must be first flush samples. There's a very specific protocol on how to take these samples. A second type of contaminant I'd like to point out is the disinfection byproduct. With lead and copper, the source of that is usually corrosion of pipes, and so the samples must be taken at the tap. For disinfection byproducts, these typically form in the distribution system. So these also have to be taken away from the water treatment plant. These form when free chlorine reacts with natural organic matter, NOM, or when bromide, which is not as common, reacts with natural organic matter to form trihalomethane, haloacetic acid, HAAs, or other disinfection byproducts, which may include bromate or chloride. You may recognize one trihalomethane as chloroform, and you may recognize that as being something that you don't want to be exposed to. Disinfection byproducts are carcinogens, so this is why these are regulated. They have very low maximum contaminant levels in the parts per billion range. These must be detected in the distribution system, and they form as a byproduct from disinfection itself. In order to reduce DBP formation, because it forms when chlorine reacts with NOM, you either have to reduce the natural organic matter or you need to reduce the chlorine. Yet, some chlorine residual is desired. This protects the distribution system. So in order to compact the formation of disinfection byproducts, the EPA propagated a maximum residual disinfection level, MRDLs. A utility cannot put out more than 4 milligrams per liter of free chlorine or 4 milligrams per liter of chloramines, which is also called combined chlorine. We'll review this terminology again in the water treatment unit. If you look at the Safe Drinking Water Act table, you'll see here that chloramines, chlorine, and chlorine dioxide have a maximum residual detection limit goal and an actionable limit of 4 milligrams per liter. A utility is required to sample throughout the distribution system and locate areas with high disinfection byproduct formation. There is definitely a balancing act a city must perform in terms of disinfecting and removing pathogens or microbials and preventing the formation of disinfection byproducts. The last section of the Safe Drinking Water Act I'll review is the Surface Water Treatment Rule. The Surface Water Treatment Rule establishes performance standards for the removal of protozoa, or Giardia is a common one. It also establishes turbidity standards. There have been amendments to this over time, such as the Enhanced Surface Water Treatment Rule and the Long-Term 2 Enhanced Surface Water Treatment Rule. And these are being applied to utilities over time. These rules specifically speak to the removal of Cryptosporidium. Cryptosporidium is a pathogen that has caused major disease outbreaks and is particularly resistant to disinfection because it can form a spore. So if you look at the SDWA table again, you'll see that the maximum contaminant level goal is 0, but that a treatment technology is specified. And if you look at the fine print for that treatment technology, you'll see these acronyms for the Enhanced Surface Water Treatment Rule. In class, we'll review the consumer confidence reports and focus on where samples have to be taken for the formation of lead and copper and disinfection byproducts specifically.